Good morning and good afternoon. This is Satish Shrestha. I'm with EasyPower, and I'm going to talk about protective device coordination and introduction. And this webinar is mainly meant for beginners who are about to start doing coordination or for those that are trying to do reviews. I'm going to start off by talking about some of the basic concepts of protective device coordination. First of all, we're going to talk about time current curves. There are many forms of doing selective coordination, and one of the most popular ones that is used in distribution systems is coordination of time delays and pickup settings for the purpose of having a well-coordinated system. To do the coordination analysis, we first open up a one line. This is your sample file, and this also comes with the demo or your installation of EasyPower. On the ribbon, click on the coordination button. Now, one thing to keep in mind is if your data is somehow incomplete and there is some critical information that's required for calculations, you will not be allowed to go into coordination focus. For example, let's say you have some missing information, say in this cable, and you forgot to enter the length. And when you don't have the length, you probably will not be able to calculate the impedance. So if you try to go into coordination, you'll get this error message saying there's incomplete data there. So go back and fix that problem. And after you complete your data entry, you'll be able to go into coordination analysis. So once I go into coordination, my ribbon changes and I get different tools that I can use for the purpose of coordination. I'm going to start by plotting a simple TCC curve. This is a circuit breaker. When I plot the circuit breaker curve, I get a curve like this. Now, before we go into the characteristics of different types of devices, I'm going to start off by talking about this plot area. Time current curves have current displayed on the horizontal axis and the time on the vertical axis. For most typical plots, you think of time as in the horizontal axis, but we have it, inversed for one reason. For a lot of protective devices, the trip time for either the fuse or the relay or the circuit breaker would depend on the value of the current that passes through the protective device. And so the time in this case is a dependent variable, whereas the current is the independent. That's why we flip the axes this way, and this has been the convention for many, many years. If you look at the scale, you'll see that these axes are both in log scale. So you have logarithms on the time as well as in the current. Now, inside this plot area, if you have a really small monitor, say for example, small laptop, then the text may appear very small. So if you want to zoom into a certain section, all you have to do is take your mouse and spin the spin wheel on the mouse, and you can zoom in or out as you need. If you have a desktop and a large enough monitor, then you will not need to do that. So another aspect of this TCC plot is that whenever we plot TCCs, we have to state at what voltage the reference value is, and we also allow you to scale the current. For example, if I double click on this plot area, we get format plot area, and you go to scale, and you can choose the reference voltage and the current scale. For example, this is at 100 times. If you want to set it to 1 time, so that it would be exactly in amps. So your curves are going to shift accordingly. In the plot area, we have a small section. This rectangle includes all the one-line items that you have selected for plotting your TCC. And you can choose to show or hide the title block. So at the top, you have this title block checkbox. So when I click on this, I get a title block, which can be formatted as per your requirements. And you can put in text, any comments that you want to put, give it a name to this TCC, what type of font are you using, etc. And if you have a company logo that you want to use, you can use that too. So that's just the basics about this plot area and how TCCs or time current curves are plotted. Okay, now we're going to start off with some very basic TCCs. Let's first take a look at cable damage curve. I'm going to select this cable, turn screen, and then click on the plot TCC button on your ribbon. So on the left side, you have the selected item. On the right side, you have this blue line here, and that is the damage curve for the cable. And this damage curve is using an equation based on the type of material, the size of the conductor, and the insulation temperatures. So how do we read this damage curve for the cable? So if you were to get a fault, okay, say I'm going to double click on this MCC, or you can do a right click and fault bus. So I get a total of 17.7 kiloamps. So if you look here, there's 720.7 kiloamps flowing through this cable if you have a fault on this MCC. And so let's put a marker, and we can do that by inserting SC tick mark. There's a SC tick mark. You get this dialog, and I want to put in 17.793 kiloamps at say momentary and symmetrical. So that would be your fault current. Okay, let me take it up to 30 cycle. So what we can say is, if we have a fault at this downstream bus, then the cable will be subject to very high values of fault current, and the cable will get damaged in this many seconds. So what we need to do is draw a vertical line here, and wherever this vertical line representing the fault current crosses this cable damage curve, that is the time. So this is approximately 10 seconds. So if you look at the right, there's 10 seconds out here. I'm going to change the font size for this. So to do that, go to Format Plot Area by double clicking, then go to Text, and right now we have this choice of small. You can either choose medium or large to enlarge the font size. So you can see that this is going to get damaged in 10 seconds. Now, that's the downstream side. What about the upstream side? If you have a cable fault out here, let's say. So if you have a fault on the upstream side of the cable, then any cable, the cable can see up to 24 kiloamps approximately. And if I want to insert and short circuit tick mark there, 24 kiloamps. So that would be there. So that would be the damage point, and it would take about maybe 5 seconds for the cables to get damaged. So what this tells us is we need to use protective device to clear the fault before the cable gets damaged. And the earlier we can have the protective devices, whether it's fuses or circuit breaker, trap the circuit, the better it is. So that's how you read thermal damage curves for different equipment. So that's for cables. Next we'll go into looking at transformers. ANSI C57 standard provides several damage curves for transformers, and we model all of those. So if you look at the dialog for this, see that there are different types. Right now this is of oil type. So as per the ANSI C57 standard, for dry type there are 2 categories, and for oil type there are 4 categories of transformers, and these categories are primarily based on the kV rating of the transformers. And so you can plot the damage curves for these transformers. I'm going to select this transformer and plot TCC. So that's a transformer damage curve. The top section where we have this little bit of curvature here, that is the thermal overload damage curve, and towards the bottom is your high fault current, a lot of magnetic stresses, and that's the damage curve for that. Let's take a look at some of the options for damage curve. When I double click on the transformer icon, I get this dialog, the transformer dialog, and in the TCC tab you have different checkboxes. So when you say you want a plot for 100% withstand TCC, what it means is this is primarily for a 3-phase fault through the transformer. So fault on the secondary side, how much fault current can the transformer withstand. So this dotted line on the right side, that is the 3-phase fault damage curve. And the second checkbox here is plot unbalanced deviating, either 58% or 87%. Now, I'm going to bring this dialog to the right side here. If you look at this transformer configuration, you've got Y grounded on the secondary side. So if you were to have a line to ground fault, then to protect this transformer against line to ground faults, you would need to have more sensitive protective devices on the primary side. And the reason for that is this is a delta to Y grounded system. So if you look at the calculations, per unit calculations of how currents can vary with the type of fault, you'll see that for a full 1 unit current, you will get about 58% current on the primary side, and that's where this 58% comes from. And 87 is for line-to-line faults. So if you want to show just the 3-phase fault, then all you have to do is uncheck this and you will get this. Next, there's this checkbox for use frequent fault curves. Now, if I uncheck this, let's see what happens to this. I'm going to click on the apply button. So there's a difference between OK button and apply button. Apply, this applies the changes that you made to the dialog and gives you a new curve or a refreshed curve. And when you click on OK, it applies the changes and closes the dialog like that. So if you want to keep the dialog open and try out different things, what happens when you change different kinds of options or data, then just hit on the apply button and you can see all the changes. Okay. And towards the bottom here, you'll see a small circle with a dot inside it, and it says, inrush. So whenever you energize a transformer, initially you get considerable inrush current because of the magnetic saturation of the core, and it will last several cycles. So by default, we have the value of 8 times full load amps of the transformer seen on the primary side, and lasting approximately 6 cycles. But this is something that can change. So based on your conditions, that would be the type of transformer that you have, the switching angle, when do you close it in, what kind of voltage do you have, because higher the voltage, higher the inrush. Because there's more saturation because of the voltages. So there are different factors, and there might be other factors like a residual magnetic effect, which is very difficult to measure, almost impossible to measure. So it's hard to predict what exactly the inrush current might be, but this is a ballpark estimate, and based on your experience, you can just change it here in the dialog. At the top, you have a tick mark for transformer. This is the full load amps. Now, if this is, let's see what kind of transformer this is. This class is OEFA. So there's forced cooling, and because of that, you have additional capacity. Okay, without cooling, you have just 1 MVA, and with cooling, forced cooling, you have 1.288. And so when we plot TCCs, we can choose what kind of affiliate tick mark to use, whether to use, just the uncooled, self-cooled rating or the forced cooled rating. And that changes the tick mark at the top. So those are some of the characteristics. Frequent fault curves are again defined in the ANSI short circuit standard. And when we use frequent fault curves, we are a little more sensitive. And we bring the damage curve at higher fault currents to smaller values there. Okay, next we're going to talk about motor damage curves. I select this motor on the one line and plot TCC. So we're going to take a look at some of these items on the TCC plot. The damage curve for the motor is usually estimated by this. See this little bit of slope. It's like an I squared T line, straight line here, passing through a circle with a dot. So this is our key indicator, the circle with a dot, and this is placed at the lock rotor amps. Now, you're all familiar with lock rotor multiplier. Typically, for induction motors, we use a value of 6. Like when we start the motor, it initially, the starting current is very close to 6 times. So that is, the approximately the lock rotor amp. And so the maximum stall times are specified by the motor manufacturer, and this can be corresponding to the motor class, like you might have class 10, class 20, class 5, etc. And so that corresponds to the stall time of the motor. So I'm going to double click on this motor icon. So I get this dialog. So you need to specify the stall time in order to uh, plot the damage curve. So the basic assumption is that if the motor has the capacity to withstand this much of starting current or the lock rotor current for, say, in this case, this is a 10-second. Let me change the scale of the text so that it's larger. So this is a 10-second stall time. Then what we can say is for smaller currents, the damage curve can be extrapolated as an I squared t is equal to constant line. So this is an I squared t constant line. And in the dialog we have specified, draw this thermal limit curve up to 40 seconds. So it's going upwards to 40 seconds. And if you want to change that to a different value, a higher value, you can do that. Okay, so that's the thermal damage curve for the motor. Another thing we want to look into is the motor starting curve. Typically when you're starting induction motors, you have the huge inrush, maybe 6 times or whatever it's based on the lock rotor impedance value. Let's take a look at the characteristics. Initially starting the motor, there's a little bit of DC offset. Just like during a short circuit, any transient is always accompanied by a little bit of DC, which decays over time to 0, and it decays fairly rapidly. So this has a little bit of DC offset. This is the lock rotor current. And this is the full load amps of the motor. So it starts, or when you start a motor, it starts off with the lock rotor amps, and after some time it accelerates, and as it picks up speed, the current through the motor decreases, and finally as it gains the rated speed, it comes to the rated amps or the full load amps. So that is the starting characteristics of the motor. And we have different types of motor starting characteristics here. And so motor starter type. So this is the full voltage, or this is also called direct online motor starting. And we have auto transformers, part winding, Y delta, and reduced voltages. So based on the type of starting, you can choose your motor starting type, and that will change the shape. For example, if you have a Y delta starter using contactors, then you can hit apply. You'll see the curve change. So the lock rotor amp reduced. So when you're starting, you're in the Y configuration windings for the motor. That gives it less voltage and therefore less inrush. And this little spike is just to represent the switchover from Y configuration to delta configuration. So there are different types, and you can give it a try there. Typical induction motors might have lock rotor amps of 6. That's why we have the default value of 6. If you have a motor that is different class, then you can change the lock rotor multiplier accordingly. Asymmetrical offset of 1.6. This bottom section, see this little slope here, that defines the asymmetry during the inrush. And this 1.6 is for very, very large horsepower motors, thousands of horsepower. And for smaller motors, it might go down to 1.2 or so. So you can change that value as needed. Okay, so that is just a primer on damage curves and motor starting curves for motor. One thing we have to look out for whenever we use trip protected device is we want to avoid nuisance trips, because we have such a huge inrush during the motor starting. We want to make sure that the protective device, whether it's a fuse or a motor circuit protector or circuit breaker, does not trip. So we need to coordinate that, and we'll talk about this in a short while. Okay, so we'll move on from damage curves to protective device time current characteristics for different types of equipment like fuses and thermal magnetic breakers, solid state trip breakers, relays, motor overload relays, etc. I'm going to start off with fuses. Okay, this is a medium voltage fuse, and so this says this is SNC as the manufacturer, SMU20. I'm going to double click on it to look at the dialog. One of the things, again, just to repeat, is that before you can plot TCCs, you need to make sure that you have entered all the data. So for fuses, the requirement is you need to do manufacturer, type, style. You need to have the checkbox, plot phase TCC checked. And for high voltage fuses, you have to select the model, the library KV, and the size. So all of these must be selected, otherwise the software will not know which curve to pull out from the library. And if you have low voltage fuses, if you have low voltage fuses, we do not have model and library KV, but this manufacturer, type, style, and the size needs to be filled out correctly. So we will go into selecting the fuse and plot a TCC. Okay, just to see how to read TCC for fuses, if you have a fault, okay, I'm going to insert a tick mark. Say you've got 10 kiloamp fuse, or maybe 1 kiloamp for now, just to make it simple. So that is my 1 kiloamp mark. I'm going to zoom in. So 1000 amps. If I drag this up, so what this is showing is based on the manufacturer published curve. Okay, I'm going to hit the control key. If you hit the control key, this cursor changes into a crosshair, and maybe it's a little bit easier to read the graph here. So there is an indicator here at the bottom. So I'm going to take my cursor there. See this? Just keep your eyes out here at this section and you'll read the coordinates there. So based on the cursor position, I can read my coordinates. So this is saying approximately at 1000 amps, I'm getting 0.019. So in 19 milliseconds, in approximately 19 milliseconds, the fuse will start to melt. So that's how we read it. So question is, how long will it take before the fuse is going to clear for sure? And so we just have to take this up, okay, and put a cursor here. You'll see that this is approximately, if you read on the status bar at the bottom, so at 1000 amps, it's going to be approximately 0.045 seconds or 45 milliseconds. So this bottom section is called the opening curve or minimum melting time, and the top section is usually called the total clearing time, and this includes all the tolerances and margins to guarantee that the fuse will clear the fault anywhere in between these 2 points. So you can do similarly for different fault levels. So looking at this fuse curve, what we can say is this is an inverse curve. And we often use the term inverse curve, meaning higher the fault current, the faster the fuse is going to clear the fault. So if you look here, we're talking about 45 milliseconds for 1000 amp fuse, 1000 amp fault current. If you have 100 amps, so 100 amp would be placed out here. Let me insert 100 amp. I'm going to set it as 0.1. Remember that all fault currents are always specified in kiloamps here. So short circuit current of 0.1. And I'm going to drag it up using 30 cycle. I will zoom in just a bit. And when I look down below here, I can read from the cursor that at 100 amps, I get about 2.69. So 2.69. So you can see that the inverse curve always gives you faster time for higher fault currents. Let's take a look at a low voltage fuse. In this sample file, I don't have one, so what I'm going to do is I'm going to go back to the database edit focus and insert a fuse. So this is a fuse switch from the equipment palette. And I'll just select some fuses. Say I'm going to choose F Busman and say FRS R RK5, a popular fuse, and say it's a 600 amp. So I'll select this fuse, go into coordination focused and plot TCC. So they, fuses kind of look similar. There are some cases where you might find, just a thin line being represented and not a thick line like this without a band. And sometimes there are cases where manufacturers do not publish both minimum melting and total clearing curve with a thick band. This is published average melting curves, and that's why we represent it as a thin line. And what we need to do in coordination is just assume some kind of margin or tolerance, plus minus 10% or whatever the requirement is. Okay. Next thing I'm going to do is talk about thermal magnetic breakers. I'll double click on this breaker here. So this is a GE THAK 400 amp frame breaker, and so it's got adjustable instantaneous settings, and I'm going to plot TCC. So that's what the thermal magnetic breaker looks like. So in distribution, most of the breakers that you use for panel boards might be similar to this kind of curve shape. You can take the cursor right over any adjustable setting. So if there's an adjustable setting and you take over it, take the cursor over it, you'll see that double-headed arrow there. That means you can adjust the settings. So just like using the mouse, I can drag it left or right. And later on when we talk about how to coordinate different devices, we'll be doing more of that. So in the thermal magnetic curve, let's just look at some of the properties here. The top section, see this curve more like a banana shape here. This is the thermal trip section. And or you can also call it long time. And at the bottom here, this is the instantaneous trip. The vertical column represents the pickup, the instantaneous pickup, which in this case is adjustable. In some cases, thermomagnetic, it might be fixed, meaning there's no adjustment available. And towards the bottom, this is the minimum time the breaker needs to clear the fault. And these are all based on manufacturer published curves. Okay. So if I look at the bottom, what I can see here is that based on the manufacturer curves, the breaker will start responding at approximately 0.01 second or 10 milliseconds, and it is guaranteed to clear the fault in this time. So in this case, that's around 25 milliseconds or 0.025 seconds. So what happens if you have a fault at, say, 1200 amps? So I'm going to insert a tick mark here. So 1200 amps fault would be 1.2 kiloamps. So I'll zoom in just a bit here. So looks like, this is the instantaneous pickup. So there's a chance that it might trip fast, but it's not guaranteed because it's within this tolerance. So if you have a fault that's within this vertical band, then for the purpose of arc flash calculation, we assume that, the worst case might happen to be instantaneous will not trip, and therefore it's going to trip only on thermal at this very top. But for coordination analysis, what you'll need to do is you'll need to look at possibilities. It can trip anywhere from this left part of this vertical band to the right part of this vertical band. And so we have to keep that tolerance in mind when we coordinate different circuit breakers or fuses. Next, I'll take a look at a solid-state trip circuit breaker. Let's open this dialog first. So this is a GE AKR circuit breaker using Microversa Trip Plus, and it's a 1600 amp sensor and plug. And it's got some settings like long time pickup setting, long time delay, short time pickup setting, and the short time slope, delay slope, whether it's in or out. And we have 3 different possible settings, and we've got the intermediate setting here. And pickup is blank, that means there's no pickup, it's turned off. Again, make sure that your data is complete in the settings for these phase trip setting. And if you have a ground, which you're required to as per NEC, you can also have this. Check this box to plot the ground curve. And whatever your pickup setting is, read it and model it accordingly. Okay, I'm going to select this breaker and plot TCC. So this is what the solid-state trip curve looks like. Earlier we talked about the different pickup and delay settings. So this is the pickup, long time pickup setting at the very top. This is the long time delay setting. This is the short time pickup. And here, this is the short time delay setting, which can be adjusted. Okay, typically short time delays go up to half a second or 0.5 seconds. Now, we had the instantaneous off. If the instantaneous was on, then you'd probably have curve going down here. So let me, and for now, I'm just going to choose a setting here. So this is the instantaneous, the vertical band is the instantaneous pickup. And this is the minimum time taken by the circuit breaker to clear the fault. So in this case, this is 0.05 seconds or 50 milliseconds. And so that was just to show you what the instantaneous pickup and delay looks like. What I'm going to do is set it back to original. And later when we talk about coordination, we can, probably discuss why we want the instantaneous turned off for the main breaker in the switchgear. Okay. We had filled out the ground trip information too, so if you want to bring it back, you just have to check this box and it's going to bring it back. Now there's another thing you can do. We have an icon at the top. This is for view or display. So you can choose this drop-down menu, view phase coordination, gives you just the phase curve. And if you choose ground coordination, it gives you just the ground curve. If you want to view both, then do phase and ground coordination and you get both. So so this side left curve is the ground curve. I'm going to adjust it. There we go. Ground pickup, ground delay. Now I squared T in and out. What does it mean? I'm going to open up the dialog. You'll see there's this I squared T out. Say this is a flat delay for short time delay. If I change that to in, see what happens. Then I get this slope, and this is an I squared T line. And a lot of solid state trips have that option of choosing between in and out, and this helps to improve coordination between different protective devices. And it comes also closer to the damage curves because most of the damage curves have a I squared T characteristics. Apart from dragging the curves and adjusting the settings, you can also adjust the settings through the dialog. For example, let's see, this is at long time delay of 2. So I'm going to change that to 4, see what happens. When I hit apply, you'll see that this curve shifted from 2 to number 4 position. So that's another handy way of doing things, keeping the dialog open and changing the settings and hitting the apply button and see how it affects your coordination. So that was the solid state trip. And next we're going to briefly talk about motor overload relays. Motor overload relays are not modeled as separate objects because for the purpose of short circuit analysis and equipment duty calculations, they need to be, these motors, overload relays need to be coupled with a circuit protector such as motor circuit protector, circuit breaker, or a fuse. What we've done is we've bundled that information into either the fuse dialog or the circuit breaker dialog. So let's take a look at this. This is a fuse dialog, and in that is the motor overload relay data. So if this fuse and the motor overload relay is feeding a motor, then you just use this checkbox, plot motor overload relay TCC. Then you go on to specify the manufacturer type and style. Say you just go for P. So type in the full load amps and the service factor and click OK. Then I go into coordination. So that's my motor overload relay curve, and this is my fuse curve. So if I want to bring this down, so there's a little bit of clipping out here so that you have a composite curve. So that's a combination of motor overload relay and the fuse curve. We can come back to it later when we talk about motor circuit protection. And next thing we're going to talk about is plotting TCCs for relays and see what they look like. In this line, on the primary side of the transformer, I've got CTs feeding relays. So I'm going to select this relay and plot TCC. So this is what a relay curve looks like based on the settings. At the top, you have the relay pickup for time over current. And so if you look at the relay dialog, you specify the manufacturer and the type, and you specify the device function. At a later time, we'll be discussing more in depth about different types of relays and relay coordination. For now, this is just a very brief overview. And in the settings tab, you can choose various settings. Like first, you have to choose what kind of range it is. Typically, one set of relay will have just one type of range. What we've done is these are not, if you have one relay, the different ranges that you get is not it's not a choice for all the relays. What we've done is we've bundled up this information, and just for the purpose of organizing and keeping it simple, we have put in the different ranges for relays in the same dialog. So choose the range and then choose the pickup, and choose what type of curve you have. So for old-fashioned induction disc relays, it might be just one type of curve shape. You're very fixed on what kind of characteristics you're going to get. But for modern relays, and specifically digital relays, since they're going to be programmable, you can put in a lot of equations. You can also put in your own relay curves and have a different variety of options there. So you can choose different types of curve shapes. And this is the time delay or time multiplier for the curve shapes. Then towards the bottom you'll see instantaneous, and that is either the plunger type instantaneous, or it could be an electronic or digital fast tripping action for the relay. So these are some of the settings that you'll typically see for relays. So on the TCC, so this is the tab. So you can just drag it and change the pickup setting as needed. You can change the time delay as needed. And same thing for instantaneous pickup. And so you can also change the instantaneous pickup and the delays. So let's set it to a slightly different value. 0.1. Click apply, and you'll see that it's moved to 0.1 second delay. Okay, so that's what a relay curve looks like, and you can have ground relays and phase overcurrent relays, and we'll talk more about this at a future time. Now, so the software comes with a very large device library, and let me show you what the device library looks like. I click on the E button at the top left corner and choose Open Library. So the library file name is stdlib, or short form for standard library. So when I open that, I see different types of equipment listed. Let's take a look at high voltage circuit breakers. Now, high voltage circuit breakers don't have, curves associated with them, but what we do is the relay that has a trip curve, once it's time to trip, it sends a signal to the circuit breaker to open up the circuit. So that's what high voltage breakers do, that is obey the command of the relays. Then fuses, we've got a long, lots of different manufacturers and lots of different types there. So if you want to add it, add any types of new fuses on your own, you can do that. If you want us to do that, we can, add any type of fuse that you're looking for. We have some engineers here continually adding to the predictive device library, and this has grown rapidly over the last few years based on demand from the users. So low voltage fuses, we've got different varieties there. If you were using Busman or Ferrashawmut or whatever, they're all there. And so there's the molded case circuit breakers. Okay, and got solid state trip units. Earlier we were talking about microburst trip plus. There it is. That's kind of a very quick glance at what the library looks like, and the library is totally customizable. You can modify any information there as needed. So back into the coordination analysis. Earlier when we plotted TCCs, we did a little bit of formatting. For example, we formatted the text, and you can do different things like scale if you want to change the reference voltage. Now, going back to reference voltage, let's take a look at transformers. When you plot a transformer damage curve, there are several ways to look at it. Do you want to see the currents from the low voltage side or from the high voltage side? Typically, by default, when we plot a transformer, we tend to go towards the lower voltage side, and that becomes the default. So this is 480 volts, which is referencing the secondary side of the transformer. If you have relays upstream and you want to coordinate with upstream medium voltage relays, and you want everything to be referenced to that, you can change that. And the way to do that is just double click here and scale. So let's say your medium voltage is 13.8 kV. All I have to do is type in that reference kV, and you'll see that when I click on OK, you'll see the curve shift. And this curve shifting is automatically adjusting the amp values, because as you go higher up, based on the voltage ratio, your current is going to be inversely proportional to that, and we do that scaling automatically. So you can choose what voltage to view it from. And other types of formatting here, you can change the grid lines, And if you have multiple TCC curves, you can either make it opaque or semi-transparent. And you can do some borders and fill colors and stuff like that. Okay, we're going to start off with basic protection principles. And let's go into protecting this motor. We've got a circuit breaker here protecting this 250 horsepower motor. I'm going to select these two items and plot TCC. Okay, now let's say we had the pickup very low. The lower the pickup, the safer it is, because you pick up and you're guaranteed to trip faster. But the problem is when you're starting motors, the motor starting current is very high, and you can see that starting current is on the right side of the protective device trip, instantaneous trip, and that's not good, and it's going to trip the circuit breaker. So what we need to do is when we start the motor, circuit breaker trip curves needs to be on the right side of the motor starting curve. Now, at the same time, another thing we need to be careful about is this is supposed to protect the motor circuit, this thermal protection. So the long time delay here can be adjusted so that the tripping time is faster than the stall time or the I square T damage line. Earlier we talked about the I square T damage curve for the motor. So to properly protect this motor, this long time delay band or the motor overload relay curve needs to be on the left side of this thermal damage curve. So those are some of the requirements. Another thing is, let's see this. If you take it too high, you'll see that this is not doing a good job because it's not protecting against thermal damage. So you'll probably need to set it back just a little bit higher than the motor full load amps. Okay. Next, we're going to take a look at cable protection. So this is a cable and it's fading other loads, NCC, so we want to make sure that this circuit breaker adequately protects this cable. So I select the circuit breaker and the cable at once and plot TCC. And you can see the cable damage curve is on the right side and the circuit breaker curve is on the left side. So it looks like this is well protected. It's a lot of gap. Now we would have problems if this curve was on the right side. If the protective device, or the circuit breaker curve was on the right side of the damage curve, that would be a problem. So as long as you're on the left side, you are going to trip before the damage point for the cable is reached. Now let's take a look at transformer protection. I'm going to go with a very common case, that is a transformer being fed by a fuse. Select all these items, plot TCC. So there's your transformer damage curve. Let's see what type this is. This category 1, I guess. And this is A. Okay, that's the dry type transformer. So this is a delta to Y grounded, and again bringing back the point of unbalanced derating. So the line on the right side is for three-phase fault. On the left side, the solid line is the damage curve for line to ground fault when you're protecting from the primary side. So what we need to make sure is that this is the fault current seen by, at this point at the bottom of this dotted line, this 2-second. That's the fault current seen by the transformer if there's a fault on the secondary side. And we need to make sure that before this damage point is reached, the primary device, in this case the fuse, will clear the fault. So let's take a look at that. So when I fault, what I did was I double clicked on the secondary side bus and I got the fault current. So that's my fault current. And so you'll see that this fuse curve got clipped at my fault current. Okay. And you can see that before the damage point is reached, the fuse is clearing the fault. So it's doing a good job of protecting. Now, question is, what about overloads? If there's a mild overload, is it going to protect? Now, in most cases, you will see that a lot of distribution transformers are not really well protected for mild overloads. And so this is usually the practice. And when you have fuse, there's less control over it. You know, the fuse shapes are have such characteristics that, you know, it's impossible to get all the desired settings to protect the transformer fully. In the case of relays, and you would have relays protecting transformers only for large transformers, you might be able to get some more, you know, variety of settings to closely protect the transformer against mild overloads as well. So another point to look at is when you select fuses or any, you know, circuit breakers or any protected devices, we need to make sure that the inrush current is on the left side or below the tripping. If the trip device is faster than this, you know, inrush point here, then you'll get nuisance tripping upon energizing the transformer, and we need to avoid going into that nuisance trip condition. So in this case, the fuse is taking longer time to melt than the inrush time here. So I think it's doing a good job of protecting this transformer and allowing the inrush current to pass through as well. Okay, now whether you choose fuses or relays, the protection principles are very much similar. You know, you have to watch out for the damage curve, and you've got to watch out for this inrush current. Okay, so we talked about motor protection, cable protection, and transformer protection. Next, we're going to talk about, you know, selective coordination here. What I'm going to do is deactivate this fuse for a second. I'm going to go back to database edit focus and deactivate. So whenever you deactivate an item, you're not deleting it, but you're saying exclude this from any type of analysis. So if I go and, you know, plot circuit breaker items here and this switch gear, I've chosen the main and these feeder breakers here. You'll see that the fuse curve was not plotted, and that's mainly because it's been deactivated. Okay, so here is the case we're looking at. If you have a fault downstream to this breaker, feeder breaker BL2, you want just this breaker to clear the fault. You don't want other breakers, the main breaker, to trip. And so basically the principle of selective coordination is, you know, making sure that only the necessary breakers trip while all other breakers remain in service. So you want the other feeders or other circuits to remain in service while only the faulted, you know, area should be removed from being in energized state. So that is the goal of selective coordination. And now when we do protected device coordination, I think one of the easiest and simplest way of doing things is using TCC plots and coordinating with time and pickup. So we're going to take a look at how we can adjust the pickup and the time delays for different settings to achieve coordination. So in this TCC, you'll see there's some color coordination. See, the breaker colors are different. For example, in my case, this is showing up as purple, and this is slightly green or teal, and this is blue, and this is more green. So, and they correspond to the color of the curves. So that's what we call sync with TCC colors, and that's an option in the TCC options. So if you go to TCC options, sorry, not TCC options, but coordination option. If you go to PDC option, see sync TCC monoline colors to TCC colors. Okay, and that's how you get that. If you uncheck that box, you'll get everything in black here, or whatever the default color might be. So we're trying to coordinate this main breaker with these downstream circuit breakers. So right now, you'll see that this purple one is the main breaker and these others are feeder breakers. Now, they are coordinated. There is no overlap. So what we're trying to do is make sure there is no overlap. If there's an overlap like this, there's a small amount of miscoordination there. Okay, and we probably want to avoid that. And if I come down like this, there's a small degree of overlap there. If I have I squared t is out, there's a whole lot of overlap. So what we want to do is avoid overlap and make sure that the upstream circuit breaker is on the left side, on the right side, sorry, of the other feeder breakers. So I'm going to set this to max. So in order to coordinate, you just have to drag your settings and make it clear of the other devices. Now the question is, I've got feeder breakers here crisscrossing. The curves are crisscrossing. Question is, do I need to fix that? Since they're on the same level, you do not need to coordinate feeder breakers with each other. You only do between different levels. So I would say main is one level, all these circuit breakers are second level. So you have to look only between upstream and downstream circuit breakers or fuses. So these can be left as it is, it's fine. Now, apart from looking at phase coordination, if you have ground trip, then you'll also have to look at ground coordination there. And just to repeat, if you want to see ground coordination grips, choose this display option there, and you can see ground curve. Let's see why it's not there. Okay. And right now you're not seeing any ground curve, but if I choose line to ground fault, then you will see the ground curve appear. And the reason for this is we use TCC clipping automatically. So what exactly is TCC clipping? I am going to illustrate with a different example here. Let's see. Okay, let's take a look at this. If you needed to, now in this case, typically, since these are all in line and there are no parallel breakers, you probably don't need to coordinate this fuse with this circuit breaker. But if in case you had multiple breakers, feeder breakers, and you needed to coordinate, then we can use short circuit clipping and short circuit tick marks to help us as a coordination tool for selective coordination. So let's take a look at what we're doing here. Say this breaker curve, I'm going to double click on this and go to short circuit tab. There's this TCC clipping, use momentary current. So it's using this momentary or half cycle current to clip it from the right side. And the reason we want to do that is the maximum current that this circuit breaker will ever see. So we do not need to show any part of the curve that this breaker will never see. So any fault current on the right side or any curve on the right side does not need to be displayed. That's the maximum it can see. What happens if we do not use TCC clipping? If we set it to none, see this continue forever, and it shows that, hey, there's some overlap out here. Now, that may not be the case at all, because if the maximum fault current is limited to 10 kiloamps, then you can say that, hey, this is well coordinated. There is no overlap between those two because it's impossible to get a current in this region. So it's better to use this tool and use the TCC clipping. So when I hit apply, it clips and you see that it's all clear here. So that is a tool for coordinating based on pickup and fault current levels. So we looked at two different methods. One is looking at the short circuit values seen by each of the predictive devices. The other one is changing the time delays and the curve shape. Now another tool we have is what we call sequence of events. Let's say we faulted a bus. Okay, and when we fault a bus, in the coordination focus, we can choose sequence of events. Click on that and you'll get trip times next to upstream protective device. So for fault on this bus, the first item to trip is going to be this BL2. It's going to trip in 0.19 seconds. And that's the fault current it sees. Okay. This main circuit breaker trips in 0.34. Okay, based on this current. As we move upstream, then there's this relay. It says 0.529 kiloamps. It trips in 0.1 seconds. And it's indicated red. Red is a warning color. Okay, so we need to watch out for miscoordination there. That indicates miscoordination. Next, it says 1,000 seconds. Well, 1,000 seconds also means it never trips. So this is very high upstream, and based on this pickup setting, this fault current is too low to trip. Okay, so that is the sequence of events, results displayed on the one line. And it might be more beneficial if we saw it as a report and did a little bit of comparison. To create sequence of events, go to PDC, Options, and you get this dialog, Coordination Options. Check this box, Create Sequence of Events Report. Okay, so when you fault this bus again, you can go to Window and you'll see Sequence of Events Report. Choose that Sequence of Events Report, and there's your report. So for that particular bus fault, that is bus called MCC1, which sees a total of 20 kiloamps for three-phase fault. you will have different devices, tripping at different times. And so these are the trip times for these devices. And this is the comparison between the upstream device. Okay. And so this is the desired minimum coordinating interval. And so anytime that interval is not met, we give out a warning saying, well, it's not properly coordinated. So that's your sequence of events. Now, talking about relays, when we coordinate circuit breakers, it's just, we just have to look for daylight through these different, between the gap. As long as there's a little bit of gap, visually we can say, hey, it's well coordinated. In the case of relays, it's slightly different. And we'll look at why it's different. I'm going to plot these two relays. So in this medium voltage switchgear, you've got the main relay on the main side, incomer side, and you've got this feeder going out, and they need to be coordinated. So I plot TCC curve for that. Okay, so there's your downstream relay, and this green one is your upstream relay. And so the question is, how exactly do we do coordination? Now, there are a few things we need to account for, and they need to be done in addition to looking at whether the curves are overlapping or not. Now, it looks like they're overlapping, but there's some other things that we need to consider are primarily the relay tolerance. If you look at the relay curve, there's just a very thin line, and that's been the practice for a long, long time. And so it does not have margins as, or whatever we call it, for tolerance. So fuse curves and solid state trips and thermomagnetic breaker curves, they had a tolerance, very thick band, so it accounted for minimum and maximum clearing. In relays, that's not the case. So what we need to do is look at how things function. We've got the relay, and they probably have a plus minus, whatever percentage margin there is. And they also send a trip signal to the breaker. The breaker takes several cycles to trip. Okay, so if I look at the breaker dialog, right-click on the breaker and choose DB info, and you'll see breakers may take 5 cycles or 30 cycles or whatever time it takes to trip. And we need to account for that. So there is a relay tolerance plus the breaker opening time. So those two things need to be accounted for. And what we need to do is make sure that it meets the minimum time gap. So I select this relay. Now on your keyboard, what you need to do is hold down the shift key and select multiple curves. So if you hold down the shift key on the keyboard and select multiple curves with your mouse, they all get selected. And after that, click on the time difference calculator at the top. So this is the time difference calculator. Click on it. When I do that, I get this marker at the bottom showing the gap between the two curves. Now, as you slide this along, you'll see this here, the seconds, the time difference increases. So whenever we place the time difference calculator here, we put it at the minimum time difference. So if you drag it left and right, if you want to bring it to the minimum, just take the cursor over the red arrow and double click on it, and it takes you automatically to the minimum point. So you'll see that the minimum is 0.21 second. And so the minimum required is, let's say this is a 5-cycle breaker here to clear the fault. And so the relay tolerance is, say, 100 milliseconds. 100 milliseconds plus 5 cycle is equivalent to 83 milliseconds. So that's a total of 183 milliseconds, or 0.183. We've got a time gap of 0.21, so we're pretty good. 0.21 is greater than the minimum required of 0.183. So we say this is okay. If the relay time difference was less, for example, just 0.1, that would not be okay. What would happen is, before this breaker got a chance to clear the fault, this relay would trip, and that's going to be a miscoordination there. So you would probably want to drag it up to a higher value, and the gap needs to be, the minimum time difference needs to be at least 0.183 seconds in this case. So depending on the type of relay, you would want to set your minimum time difference there. So that's how you do relay coordination. And once you've done your coordination, what you can do is click on this report, and you'll get a report of all the settings for the different devices you've selected when you do it from the online. If you have a TCC plot, then you can also create a report for that TCC plot. Just click on report, and just the items in those TCC, all the selected items will get created in the report there. And just to wrap up this session here, so apart from doing coordination with manual effort, we also have a feature called Smart PDC, which will automatically do the coordination for you. So I'll just give you a brief introduction of how auto coordination or Smart PDC works. So let's say I do plot all these, equipment and plot. So I select these breakers, and I click on Smart PDC button, and you'll see the curve shifted automatically. And apart from, computer running its algorithms to change the setting, we'll also look at what exactly it's done here through the report. So if I go to Window and choose Auto Coordination Phase Report, it gives you a very detailed report of what were the predictive devices that it was trying to coordinate with, and what were the equipment it's trying to protect. So we're trying to look at two things: protect downstream equipment, and we're also trying to coordinate with downstream breakers and fuses. So it gives you the old settings and the new settings. It also gives you the reason for why it set it to that particular pickup or delay. And so this is a very good guide or a checklist for doing your coordination studies. Typically, when you have a large plant or facility to do studies on, it's very easy to miss out a few details. But this gives you a really good benchmarking checklist so that you don't miss out any details. So anytime you're trying to do protection, it gives you a list of full load amps, what's the log rotor amps, and what are the criteria based on NEC code factory calculations, and what are the minimum settings you have to do, what are the maximum settings you're allowed to do. So that's a snapshot, very brief snapshot of what Smart PDC or auto coordination does for you. And you can do it for circuit breakers, you can do it for relays. And they are following the NEC rules right now. In future, we will be supporting IEC as well as Canadian Electrical Code in doing Smart PDC. So what I'm going to do is I'm going to wrap up this session right now. I will respond to all of the questions and by email at a future time. So thank you very much. So if you do have any questions, please feel free to send them to me. You can send it to techsupport@easypower.com, or you can send in the questions to Satish at easypower.com. Thank you very much for your time. At a later time, we will be discussing more options on coordination, and we'll also take a greater look at deeper look at what Smart PDC can do for you. And we'll also try presenting some case studies of some of our studies we've done in the past, and maybe discuss some interesting problems and solutions. Thank you very much, and goodbye.